Today we will talk about cutting speed and how to transform this theoretical number in something tangible, something practical to be exploited in the processing. We will use it to know the right number of revolution suitable for performing a good chip removal just after the opening. First of all, what is cutting speed? Well, cutting speed is nothing more than the space that the tools travel in the material in the given period of time. Generally, this value is expressed in meter per minute. It's generally found as a parameter in the table provided by who sell the tools, and is indeed a theoretical number, an optimal value, but I would like to make you understand specifically how it varies in order and adapt it in the reality, because it's the final goal. But what is this cutting speed influenced? Why we found this theoretical number in the table and not another? The first factor is the difference in hardness between the cutting tool and the workpiece. A video plate like this, which remove material from a classic S235, 275, will have a different cutting speed than this classic drill of super rapid metal that cutting inox material. Therefore, it is important to understand the difference between hardness of the tool and the material involved. Second, the value is influenced by the geometry of the tools, the famous cutting edge, while working on the piece, the famous sharpness. Because if we don't have a good geometry, the chip removal is badly and generates more heat compared to the optimal situation. Thirdly, the cooling method. There's a lot of difference between a simply air-cooled system, the air we breathe, and a jet of coolant shot directly in the process area. And fourth aspect, not often considered, the stability of machine, the classic vibration. The vibration led you briefly variant of cutting speed. For example, if you have a value of 2, but during the process we can find passing from 1 to 3, and 3 is an outscale value that can will lead to unwanted problem. These are the main aspects. I don't want to enter in the marginal one because in reality are either not relevant or even not existent. So now we have a basic idea of what cutting speed is. But before showing how to transform this theoretical number, I had to add something. There's another speed called advancement speed. Briefly, the cutting edge moves in two directions. One is the cutting speed. The other is advancement speed. This speed allows the following tool to find other material that will be removed. This is important to be known because if we remove too much chip, or if the chip removed will be not go away from the tools, we have more heat. It's important to understand that the speed exists because one of the fundamental points of the processing is to keep the heat generated under control. Too much material moved means excessive friction of the piece and the temperature will be rise. Okay, let's see how we can use this cutting speed. We understand that our interest is to approach this theoretical number data, but there's no machine that you can enter this cutting speed and have it. Apart from CNC machines, but they too extrapolate this value with this formula that we are going to see. The formula say the revolution by minutes is equal to cutting speed for 1,000, all divided by pi Greco for the diameter of the drill or the piece that turn. So we make an example. If we have a cutting speed of 20 meter by minute and a drill of 10 millimeter, we got 20,000 divided by 314. The number is 636, 37. If we change the diameter of the tools by 30, we got a third of this value. If the cutting speed will rise, the number of revolution by minutes will be raised. Now this is an optimal value. In reality, machines don't have this kind of precisions. We get to adapt it at what we got. Just a CNC machine can have the right number because they have a system that adapt precisely the revolution by minutes. So we'll see an example. So we got 636. As you can see in this plate, the nearest number is 600. So we're going to set it. For have it, we have to make 1, the V, and the power to 2. We turn on, and let's see. These are 600 RPM. So now you have understand how to adjust a machinery to have the optimal number of revolution by minutes. Remember one important thing. It's very important to get close to the optimal number. Luckily, there's often a good margin of error. On the other hand, if you think about it, a drill at half of this cutting edge will have a half cutting speed, and yet we drill the same. But now I would like to add some goodies that in reality I use are the one that I actually use. You can well understand that variable number involved are 3. The cutting speed, the revolution by minutes, and the diameter of the drill of the turning pieces. There's a dancing on these 3 values. And I'm interested in understanding how much revolution by minutes quickly for setup. If you repeat this formula every time, we got an incredibly amount of time. So initially I changed this formula in this way. The 318 is 1,000 divided by pi Greco. We got a simple formula, but is still too slowly. So I have think another way to find this revolution by minutes. In this case, for example, I will divide 6,000 by the diameter of the drill, and we have 600. That is very close to 637 that we got before. Changing the tools with Vidia, I will use 8,000, and 8,000 is 25 meters by minutes. That is close to the right cutting speed that we should have with this tool. Using this kind of method, we will with time, using repeatedly this formula, you will arrive to know just by looking how much revolution will be necessary. But it's very important to metabolize and to know how we have got it. Because when a particular case happens, you will know how to go backwards in this method and understand what change to have a right value for a calculation, avoiding this way gross errors. So I hope you have understand and we will use what I've told, and we will see on next video. Bye!